So I didn't have a chance to go into medians, altitudes, and perpendicular bisectors of triangles as much as I wanted to in class. So I thought I'd make this little video for you guys. So this is from chapter 4:7, and I wanted to start off with a median. The median of a triangle is a segment from a vertex to the midpoint of the opposite side. And all that means is, if we have this triangle labeled A, B, C, then the median of that triangle would be from a vertex, which just means a corner. So this one, or this one, from a vertex to the midpoint of its opposite side. So if we choose to find the median from A, we'd have to find the midpoint of BC, the point in which it's divided in half, and draw the median from there. So that's a median. You can find another median in this triangle. Let's see, we'll do this one in blue. If we start from this vertex, then the median of the triangle goes to the midpoint of this segment, because you always go to the opposite side of the vertex. Of the vertex. So that would be that median. And from this vertex, the median would be, I'll do that one in red, from this vertex to the median, the opposite side right there. So that's all that the median is. The altitude of the triangle is a little bit different. I'm actually going to just start off with a fresh piece of paper for this. So the altitude of a triangle is the perpendicular segment from a vertex, which is one of the corners, to a line that contains the opposite side. So sometimes the altitude is actually outside of the triangle. But in our first example, it won't be. Each triangle has 3 altitudes. Okay, in an acute triangle, where all the measures of the angles are acute, which means smaller than 90, then the altitudes are all within the triangle. So we're going to draw our triangle again, and we have A, B, and C. So our first altitude is going to be the line that goes from A, that is perpendicular to this segment. Now in our median, the median has to go from this one to the middle of this segment, but the altitude isn't always going to be right in the middle. So if we draw this line perpendicular, that means it has to hit this at a right angle. So for it to hit at the right angle, it would have to and still go to this vertex. It would be about right here. So that would be the one altitude of this triangle. We can also find the altitude from this point, from point B. So we have to draw it straight down to this other line, and we find the place where it hits AC at a 90-degree angle. So that's the altitude from point B. We can also find the altitude from point C. So we look and we find, where does the line hit segment AB at a right angle and still connect to this vertex. So that would be the altitude, the 3 altitudes of this triangle. Now when you have a right triangle, things get a little bit different. If you remember, a right triangle is a triangle that has one 90-degree angle. Okay, so it looks like this. And we will also label this one, we will label this one E, D, F. A right triangle also has 3 altitudes, but 2 of them are actually the sides of the triangle. But let's start off with the one that is not a side of the triangle first. We'll start off with the altitude from D. So here we would find the line that hits the opposite side at a right angle. So this is one of the altitudes. Now when we look at point E, if we draw a line straight down to its opposite side, where it hits at a right angle, we know this is a right triangle, so we know this is the right angle. So ED is the altitude of the triangle, even though it's one of the sides. So here is the second altitude. Now I'm going to turn this triangle around this way so you can see it a little bit more clearly. The third altitude is the one that the line drawn from F. We already drew one from D, And we just drew one from E. So now we need to draw an altitude from F. And we need to find the line that, when drawn to the side opposite, which is ED, will hit it at a right angle. Well, again, because we know this is a right triangle and that is the right angle, here's the other altitude. So we have this one and this one and this one. Those are the three altitudes. And notice that two of them are actually sides. So in a right triangle, two of the altitudes are actually also the sides. Now, in an obtuse triangle, things look a little bit different. It also has three altitudes, but two of them are actually outside of the triangle. So remember, an obtuse triangle, this one is really obtuse, is one that has an angle greater than 90 degrees. So here's our angle that's greater than 90 degrees. And we will call this K, and this one L, and this one N. The first altitude we'll find is one that is actually inside of the triangle. We need to find from this vertex a line that hits its opposite side, which is LN, at a right angle. So it would be about right here. That's the first altitude. Now let's see what happens. When we look for an altitude from L, it needs to hit the opposite side, or a line that contains the opposite side. Any line that we would draw to this opposite side is not going to be a right angle to this actual segment right here. So we need to extend the segment out with a dotted line. We have to extend it long enough that we can now draw a line from L to hit this line that contains KN at a right angle. So in an obtuse triangle, this altitude is outside of the triangle, but it has to be where L hits a line containing this at a right angle. And the only place it would do that would be outside of the triangle. Now we found the altitude for K and L. Now we need to find the altitude for N. And we need to find where it will hit the opposite side. The opposite side of N is LK, or a line that contains LK. So we're going to need to do the same thing over here. We're going to need to extend that line out this way so that we can draw another altitude from N at a right angle down to this line. So in an obtuse triangle, the three altitudes are here, here, and here. And two of them are outside of the triangle. Now there's one more thing that I want to show you about from this chapter, and it is called the perpendicular bisector. And I think you could probably figure out what it is just from its name. A perpendicular bisector is a segment of a segment is a line that is perpendicular to the segment at its midpoint. So it's two things. Let's say this is the line segment. We need to draw a line that's perpendicular, but it also has to bisect this line. So the point in which this line is bisected is about right here. That's where the line is cut in half. Now we need to draw a perpendicular bisector at a 90-degree angle here. So we can say that this is line L. Line L is a perpendicular bisector to segment JK. Now, if I had drawn through the midpoint this line, that line is a bisector of JK because it does cross at its midpoint, but it is not a perpendicular bisector because it doesn't hit it at a right angle. So now that you know these three things, altitude, median, and perpendicular bisector, there are some theorems that go with this. Theorem 4.5 says that if a point lies on the perpendicular bisector of a segment, so we shall first draw a segment. This is segment BC. And if a point lies on the perpendicular bisector of a segment, then the point is equidistant. This word equidistant means it's equally distant. The distance between the 2 points are the same from the endpoints of the segment. Okay, I'm going to say it one more time. If a point lies on the perpendicular bisector of a segment, then the point is equidistant from the endpoints of the segment. So all that means is we first need a perpendicular bisector. So we're going to do this, and we'll call this A. This hits the perpendicular bisector needs to, since it's the bisector, it needs to hit BC in where it would cut BC in half. So if point A is on the perpendicular bisector, if it's perpendicular to this line and it bisects this line in half, then the distance between A and B is the same as the distance between A and C. Now you can see I didn't really draw that correctly. It's not quite the perpendicular bisector, so we'll move our little circle right here. So all theorem says that if this is the perpendicular bisector to this, then point A is equidistant between B, the endpoints of the segment, and C. This equals this. So you'll be able to use that in your proofs. Now, theorem 4.6 uses these concepts as well. Theorem 4.6 says if a point is equidistant, it's the opposite of the one that it's the converse of theorem 4.5. This one says if a point is equidistant from the endpoints of a segment, then the point lies on the perpendicular bisector of a segment. So it kind of works opposite of the one we just said. So here is our segment, and then we are going to say, we're going to put a point here, and if we measured this length from B to A, and then we measured from A to C, and if we found that AB was the same measurement as AC, then we could say that point A is on the perpendicular bisector of our original segment, BC. Does that make sense? So it's the opposite of this one. Theorem 4.5 says, if this is the perpendicular bisector, here's our segment, then a point on this perpendicular bisector is equidistant between these two. This one is the opposite. If you can prove that these two measurements right here are equal, then you can say that A is on the perpendicular bisector of BC. So there are two more theorems in this chapter that I wanted to make sure that you knew. Theorem 4.7 says, if a point lies on the bisector of an angle, then the point is equidistant from the sides of the angle. So we need an angle to start off with in order to understand this theorem. And we'll call this B, and we'll call this A and C. So here's our angle. Now we need the bisector of an angle. That's the line that cuts this angle in half. And we'll label this one Z. Now our theorem says, if a point lies on this bisector of an angle, so let's get a point on this angle. Let's do this one. We'll say this is point P. Here's our point that lies on the bisector of an angle. Theorem 4.7 says that if it's on the bisector, then it's equally distant to the sides of an angle. So this line goes to the angle, and this line goes to the angle. So we can then say that this measurement is equal to this measurement if this point lies on the perpendicular bisector. Now theorem 4.8 is the converse of that theorem. This one says if you can prove that X, this point X and this point Y, if a point is equidistant to the sides of an angle, if I can prove that this length is equal to this length, then I can say that this must be the bisector of the angle. So you can see how this might be used in the theorem. If you were trying to prove that this angle was, let's call this angle 1 and this angle 2. If you were trying to prove that angle 1 was equal to angle 2, and you were able to say, if they told you that PY equaled, let's say 4 centimeters, and XP also equaled 4 centimeters, then you could say that because these 2 points are equal, because PY, the segment PY, was equal in length to PX, then this point P must lie on the perpendicular bisector of this angle. Then, if you know that BZ is the perpendicular bisector to angle ABC, then just from the definition of a bisector of an angle, then you could prove that 1 must equal 2. So in chapter 4.7, you will use those those 4 theorems in order to prove different things about the triangle.